Hello, welcome back to the Geog 300 Geographical Data Analysis video series for WVU. We are now continuing the probability portion by looking at, and I said distributions will come back. This is distributions part 2, as it were, probability and distributions. We can have an event, and instead of just treating each individual outcome as its own little calculation, we can have a general approach using a distribution to understanding the likelihood of any and all outcomes of that event. And I'll again illustrate some of these simple examples of distributions, starting with distributions for discrete data. A distribution for discrete data, the first one, so you flip a coin 20 times. How many of those flips are going to be heads? The binomial distribution can help us answer that. Yes, 10 is the most likely answer, but it is not the only possible answer. Anything from 0 to 20 is possible. Any value in there is possible, but the middle values are more likely. This distribution, and it has a step pattern because it's discrete. The ones I drew before would be for continuous data. And I can then say the probability of it getting 13 heads, the area of this bar, relative to, as a proportion of the whole area under this distribution. If instead you're interested in how many heads you will get in a row, instead of the total number out of 20, so you flip a coin. The geometric distribution will tell you how many heads you'll have in a row. The most likely is 0. If you get a tail, that's 0 heads in a row, you're done at 0. If you get a head, your next flip has a 50-50 chance of being a tail, in which case you're done at one head. Or it can continue on. With each subsequent head becoming half as likely. So getting 2 in a row, that'll happen an eighth of the time, and stopping at 2 in a row. If you continue on to the third, then the chances of stopping at 3 is 1 out of 16, 1 out of 32, 64, 128, 256, 5, 12, 10, 24, and so on. So now you can possibly see why I had said the decreasing distribution is sometimes also called a geometric distribution. This decreasing by the same amount, half by a half, times a half again, times a half again, and so on, that's the geometric distribution. And so you can then go and say, well, what if I'm flipping a coin, how likely am I to actually get a series of 5 heads in a row? Right off the bat. And that would be 16, 32, 64, 1 out of 64 to have exactly 5 heads in a row. One, it doesn't quite relate as well to flipping coins. So I'll switch to something else called a Poisson distribution, looking at so if you're told, for example, an area floods roughly every other year. Hopefully it's in a floodplain then. So once every 2 years. How many times would we expect it to flood within a given decade? So, I'll actually change this. Say it floods a third of the time. The way I've set this up, the most likely value would be 3. 3 times in a decade. But the other values are still possible, but now, unlike that binomial distribution, which was symmetric, it was even on both sides. This, in a way, looks a bit more like a skewed version of the binomial distribution, where there's a longer tail above versus below, in part because we can't go fewer than 0 times in a decade. Those are 3 of the more common discrete distributions. and they will at times come up. The poisson especially will come up later in the course. But in many cases, we will be working with continuous data instead. There are many, many different continuous distributions. As I alluded to in the first part of the distributions, or the first distributions video, we'll look here just at the normal distribution. So we've seen this to be symmetric. Values above the mean are just as likely as values below the mean. The most common value is itself the mean. So the mean is the mean, the median, and the mode. They're all the same. And how wide this is based upon the standard deviation. So there's the main difference here is we can no longer say if I'm just to pick a simple version, the mean being 0, standard deviation of 1. To say the probability of x being exactly equal to 1.4, we can no longer use this to answer that specific question because it's continuous. The probability of any exact value is basically 0. It could be 1.4, it could be 1.399999, 1.400001. So now this doesn't really work. Instead, we're looking at ranges. I could look at the probability of x being greater than 2.9. The probability x is between -1 and 1. Probability x is less than or equal to 2.4. Any of those are valid statements. The way I would interpret this, I'll just highlight the top one here in blue. 2.9 is going to land about here. In red, I'll do this one. So anything here in this middle portion, obviously this is a much higher probability than the blue. And I put here in green, less than -2.4. All of these are valid probability statements, and it's the proportion of this small area, or this large area, or this, again, kind of small area, divided by the total area. So we can treat the total area as the probability of the event, this as the probability of the outcome I have specified. And now the frequency of the range specified, the frequency of the whole event, and I can use that to get the probability of this range. this is important information that we will then use in our next and final probability video, which will get us towards reaching a conclusion and using probabilities to start to understand some process. So again, thank you for watching. If there are any questions, please let me know by email or in class.